Hello students, so in this lecture we'll be talking about the significance of relaxation time. Now, the relaxation is basically a mechanism by which the dipoles can exchange energy with their surroundings. So, mechanism by which dipoles exchange energy with surroundings. There are two types of relaxations. One is called spin-lattice relaxation, and another one is called spin-spin relaxation. Now, the two mechanisms can be separated readily, as one being at strong field and low frequency, other being at weak field and high frequency. So, this one here, the applied field, magnetic field is greater than the internal magnetic field of the material, whereas in this case the applied magnetic field is less than the internal magnetic field of the material. So this one occurs at low frequency, whereas this one occurs at a higher frequency. The spin-lattice relaxation time is strongly temperature dependent, whereas spin-spin relaxation time is temperature independent. One other property is that this is temperature dependent, whereas spin-spin is temperature independent. Relaxation time is a time interval characteristics. It actually restores the disrupted system to an equilibrium configuration, and it is associated with the spin-lattice interaction. So if there is a time taken to restore a disrupted system, and it is associated with, and to bring it back to an equilibrium configuration, that is called the relaxation time. And if it is associated with spin-lattice interaction, the time taken for spin-lattice interaction, say, is tau 1. This is the relaxation time for spin-lattice interaction, and for spin-spin interaction, let us take for mean spin interaction. Let us take the time to be tau 2, and the tau 1 is again equal to 1 by 2w, which is equal to 10 to the power minus 4 to 10 to the power 4 seconds. So it has got a wide spectrum. Solids are actually falling into the shorter side of it. For solids, it is less than 10 to the power minus 2 seconds, whereas the higher part goes for liquids and gases. And in the case of spin relaxation, it arises due to mutual interaction between different magnetic dipoles. In different magnetic dipoles, and each nuclear magnet finds itself not only in applied magnetic field H0, but also in a small local magnetic field produced by neighboring nuclear magnets. So there are a lot of nuclear magnets, a lot of dipoles. So one of the dipoles, and remember that here the applied magnetic field is actually less than the internal magnetic field. So the neighboring dipole, suppose we are concentrating on this particular dipole. So the neighboring dipoles will have an effect on this dipole. Let's say that effect is HO local. And to this applied magnetic field, there is H applied. So both of them will affect the relaxation time, tau 2, due to spin-spin interaction. Then the direction of the local field differs from nucleus to nucleus because relative position of neighboring nuclei in the lattice and magnetic quantum numbers. So we have something called transverse relaxation time. That is tau 2 is equal to 1 by delta W0. It means that if the two spins have precession frequency differing by delta omega 0 and the initial in phase, then they will out of phase in time 1 by 10 to the power minus 4 seconds. So this is actually start of this is omega. So it is the difference in frequency which is actually equal to that if the two spins have the difference in frequency between the two spins, that is denoted by delta omega 0, and they are initially in phase. So spins which are in phase, the time taken for the spins to be out of phase then that time is tau 2, and it is equal to 1 by the difference between the frequency of the two spins, and also it is of the order of 10 to the power minus 4 seconds.